Welcome to the presentation of Group 3 about gas pressure sensor using Moiré pattern. This is our team members. And first I'm going to be introducing about Moiré pattern. Moiré pattern fringes are formed when two grating patterns are overlapped with each other. If the grating pattern is made out of straight lines, then it will produce the pattern in figure 1. And if the overlap pattern is a circular pattern, then it will produce hyperbolic fringes as in figure 2. Next, I'm going to be talking about the application of Moiré pattern. As we all know, Moiré fringe pattern changes when either one of the grating pattern moves. Based on this concept, imaging techniques of the Moiré pattern is used to locate and quantitatively measure structural deformation of big structures down to a microscale of atoms dislocation. And these data are inferred from the intensity and phase of the pattern. In this report, the application of Moiré pattern in gas pressure sensor will be further explained. Next is the derivation of the deformation measurement using sampling Moiré method. When the grating moves by a distance of u equal p over 5, the Moiré fringe in B will move by u q over 5, as shown in the after deformation B prime, where P refers to the grating pitch and Q refers to the pitch of the Moiré fringe. Thus, generalizing this gives us the equation as below. Furthermore, the phase difference in C can be quantified as change in phi, which corresponds to U, and phase change by Q also corresponds to 2 pi, which in the end will give us this equation as below. As we have mentioned before, a possible practical application of the Moiré pattern system is to serve as a gas pressure sensor. This is the setup that our group had come up with. The materials and equipment that will be needed are a balloon, gas syringe, 2 Moiré pattern grids, a camera device, and also possibly a flashlight used to improve the visibility of the Moiré pattern. Theoretically, from this experiment, we will be able to obtain a calibration graph of pressure against displacement. This means that if we monitor the change in displacement of the fringes, we can immediately tell from the graph how much change in pressure this corresponds to. There are several advantages in using this system. For example, in scenarios where high sensitivity of monitoring pressure changes is required. This is because Moiré pattern can accurately measure small changes and movements. Furthermore, this measurement could also be done with no contact, as we use the physics of optics, and this would mean that our materials and tools will experience less wear and tear, and this implies that the system will be durable and more effective. For the experimental procedure of our experiment, we will first start by calculating pressure at different volumes using the ideal gas law, PV is equals to nRT. To do so, we will first have to find the initial volume and temperature of the gas inside the balloon. And with these initial conditions, we can obtain the value of n. And then simply vary our independent variable, the volume. We can calculate for our pressure P with the following formula. And in step 2, we simply plot our results from step 1, and we can get a calibration graph of pressure against volume. This is an example of the graph. And in step 3 and step 4, it's simply the conduct of our experiment. And more importantly, in step 5, which is the image analysis to calculate the phase shift and displacement of the Moiré pattern. We first capture an image of the initial Moiré pattern when no gas is added yet, and then we can denote this image as image 1. And for each volume of gas added to the balloon, we can generate an image 2. This image 2 is where the Moiré pattern will have its corresponding new position from the addition of volume. And we know that the phase shift in the fringes is the change in position of the fringes between the image 1 and image 2. So using a image analysis software, we can overlay these images on top of one another, and then we can measure the distance the fringes in image 2 have moved with reference to the ones in image 1. And as we know, The displacement of fringes between image 1 and image 2 indicates the displacement of our flexible membrane due to the change in pressure. So we can somehow relate the displacement of our fringes and displacement of our flexible membrane. To get the displacement of the fringes, we can use the formula on the right-hand side, which is d is equals to lambda over 2 pi multiplied by the delta phi. Delta phi is simply our phase shift, which is calculated before, and also lambda is simply the measured distance between two consecutive fringes in our Moiré pattern. And since we have all the values available to us, now we can calculate for d. And then in step 6, we can use the values of d to create the calibration curve between pressure versus fringe displacement. And we reach the goal of this experiment. Thank you. Now my teammate will continue with the next part of our slides.
Due to the high costs associated with conducting the actual experiment, we have utilized programming to the greatest extent possible to simulate this experiment, aiming to explore the impact of distance rather than angle on Moiré patterns. Although we cannot be certain whether our creation is entirely accurate. We have attempted to combine applied methods. The following images illustrate the results of using pressure variation to alter the Moiré pattern spacing in the simulation. We attempted to identify the relationship depicted in these graphs, but due to our insufficient theoretical background, the generated relationship graphs are somewhat unusual, and we are still unsure of the correct correlation. From the current experimental results, it can be concluded that the Moiré pattern spacing is not entirely positively correlated with the distance between the layers. Furthermore, they exhibit a jump every kilopascal. Since these results are not as expected, further discussion is needed in the future. We hope that in the future, if this relationship can be identified, it may provide a new option for pressure measurement. Thank you.